Hey guys, so today we're going to be talking about correlation and causation and the difference kind of between the two. And then we're really going to get into correlation and looking at the correlation between two different variables and what that actually looks like. So when we're looking at correlation, researchers are really taking a look at and investigating the difference between or the relationship between two different variables. And we have our two variables that we already defined earlier in our section, which was the explanatory and the response variable. So the explanatory variable is the one that explains or is predicting the response. So the explanatory variable is the one that explains or predicts the response variable. Remember, explanatory, usually your X variable. When we're looking at our other variable, so our response variable, this is what researchers are trying to explain or what they're trying to predict. So this is what they're trying to predict or what they're trying to explain. This is their response variable. And usually that's going to be your Y value. So the two unrelated quantities are not necessarily explanatory or response, but they're going to be the variables that we're going to be taking a look at. So looking at the difference between correlation and causation. When we look at correlation, remember I told you earlier in the year to make sure that you're careful using the word causes the other to happen, or where we're correlating or when we're associating. Those are all very different things. When we're looking at correlation though, so correlation, it just describes some type of relationship. So it just says there is a relationship between. There's possibly a link. There's a tie between the two. They're related somehow. There's some type of trend that's happening, or one tends to happen. We'll say trend. That's supposed to be in there. So without suggesting that the variable affects the other. So we're not saying that one causes the other variable to occur. We're just saying, hey, there's a relationship that we are seeing between the two. The causation, totally different. Causation is indicating that one variable directly affects the other. So one variable directly affects the other to happen, meaning one causes the other to happen, one causes an increase or one causes a decrease in the other variable. There's some type of benefit, there's an impact, there's an effect. If this happens, then this happens. So making sure that we're looking at the difference between the two, but we're really going to focus on correlation. Now, when we're looking at correlation, there's actually a mathematical way to assess our correlation, and it's called the correlation coefficient. And maybe you've heard about it before in algebra. Maybe you haven't. But when we're looking at correlation coefficient, we usually dictate it with our R value. So when we use this number, we're describing our direction and our strength of this is the next very important thing, of a linear relationship only. So linear meaning our points look like they're forming a straight line between the two variables. So one is linear. Make sure it's only linear relationships. And we're going to go through all these different facts and everything too. But R represents your direction and your strength of the linear relationship between two variables. Now, yes, majority of the time, we're going to use our technology to find the correlation. And we actually did this in the Vitruvian Man activity as well, and we calculated our R value by hand. This is our R, this is our correlation coefficient. That's what we're taking a look at. In your worksheet, you're also going to be finding this by hand. So using all these different numbers and all these different values, we're going to use our calculators to find all of it. You'll fill in your table and everything, but you'll use this formula that I'm about to show you here next in your worksheet for tomorrow. So looking at the formula is, we have our R, which is our correlation coefficient. We take 1 divided by n minus 1, and we already talked about n meant. N is the number of observations. And we're going to take the summation, so the sum what we're going to do is take each individual x value, and we're going to subtract our mean from it, and we'll divide by the standard deviation of those x values. And we're going to do the same thing. We're going to multiply by our each individual y minus our mean of our y divided by the standard deviation of our y values. So what each piece means, once again, the correlation coefficient is r. Each individual x value is our x sub I. Each individual y value is y sub I. And remember, we also have n is the number of observations. Okay, x bar, y bar. X bar is our mean of our x values. Y bar is the mean of our y values. S sub x is the standard deviation of our x values, and S sub y is going to be the standard deviation of our y values. Really what we're doing, essentially, is that we are trying to find the average of the product of the standardized scores. So this is standardizing our scores, and we find the average of our product of our scores. Average of the product of the standardized scores that we're going to be taking a look at. That's basically what our R value is. And we did this before in our Vitruvian man. You're going to do it by hand as well. Remember, all of these values, the x bar, y bar, x sub s, y sub s, can all be found in your two variable statistics in that little button in your calculator. All you have to do is enter in your lists. All right, so let's talk about the correlation coefficient and some interesting things about it. So first fact is this. So if you want to get out a highlighter and highlight these facts, you may do so. So, fact 1, correlation is a number that is between -1 and 1. So your R value is going to be no less than -1 and no greater than 1. Ever. It should always be between -1 and 1. And the reason why? -1 means that there is a perfect negative linear relationship, meaning that with our explanatory on our x and our response on our y, we're going to look at a negative linear relationship. So it's going to look like our points. So remember, this is a scatter plot, but our points are going to look like a perfect linear negative relationship. So it's going to be decreasing left to right direction, negative. This is decreasing, and it's in a very strong, because that's our strength, strong linear relationship. It's perfect. Perfect straight line. Now, on the other side, we have 1, where we have a perfect positive linear relationship, where we're looking at our points increasing left to right, and they're going to be looking like a perfect linear relationship, perfect straight line. Ideally, that's what our R equals 1 and -1 would look like. Now, looking in between with R equals 0, where we have just scattered points. It doesn't look like anything. It's just scattered. So maybe we have a point here, point here, point here, point here. I can't tell if it's positive or negative or none. I just have everything scattered. Now, this could also mean that we have no linear relationship. Remember, I told you correlation coefficient responds to a linear relationship between two variables. So I may have something that looks like this, where I have something that looks quadratic. That would be an R value of 0. So, or we have a non-linear relationship at all. Oops. That's supposed to be linear. Non-linear relationship at all, where you have something like this, where it's quadratic. Or we also have that logarithmic that we were talking about. So we have something that looks like this, and it kind of tapers off. Or we have something that might look like this, where it's exponential and it increases exponentially. Some of those would be non-linear. Those would be an R value of 0. All right, our next fact is that when we have positive correlations, we will have our positive correlation between 0 and 1 and varying the strengths. Remember, your strongest positive is going to be close to 1. Just like we have here. Strongest positive, close to 1. It is a perfect positive linear relationship. Then we have different strengths. So if I have R equals 0.2, when I say there's a weak relationship, that really just talks about how close together our points are. So if I have a 0.2, I may have my points a little spread out, but I can still tell that there's a positive relationship in there. It's just weak. So I may have a point here maybe and a point here, and they're just really spread out, but I can still tell that there's some type of positive linear relationship there. I can maybe draw a straight line through there and have that line of best fit, and it's going to be positive. And we can add in a few more points if you want to. All right. Looking at a 0.5. 0.5 is going to be like the moderate. It's in between, and there's really no cutoff value that you could say that there is a weak, moderate, strong. Really, it's just using that intuition by looking at the scatter plot and kind of using like a guesstimation of what it should be. So 0.5, our points are going to be closer together, so it's going to be a little bit stronger of a relationship where I can really see that it's going to be increasing or it's going to be a positive linear relationship. So I may have points like this where I have points that are kind of close together that are kind of increasing here. I got maybe a point here, and maybe we got a point here and here, here and here, maybe up here. So they're closer together than they are in the 0.2. 0.9 is really close to 1. So we may have a lot of scattered points, but they're going to be even closer together than the 0.5. So I want to make sure that these are closer together than the 0.5. So I'll have maybe something like this, where we have points that are really close together, and they're increasing left to right. It's not necessarily going to be a perfect linear relationship, but at least the points are somewhat really, really close together, and that's what dictates that strong relationship. Now, much like positive correlations are between 0 and 1 in varying strength, so think of it as a positive R value, you're going to have a positive relationship. The weak and moderate and strong are just how close and how far together the points are. Now, same thing with a negative correlation. So negative correlation is going to be anywhere from, so negative correlations, this is fact number 3. Negative correlations are anywhere between 0 and 1, and they vary in strengths. So the strongest negative relationship is going to be close to negative 1. So our negative 9, or negative 0.9, is going to have a really, really strong relationship. It's going to be possibly really close to having a perfect negative linear relationship. So here, where points are going to be decreasing left to right, so if it has a negative value for your R, you should know that, hey, that is a negative linear relationship. It tells you the direction of which your points are increasing or decreasing. So here, we're going to have our points really close together. So just like we had with the 0.9, reverse that, we have a negative 0.9, so it gives me a negative linear relationship. And we're going to take a look at possibly having some points that are really, really close together. So we have something here, and we're just going to be decreasing with some points that are really, really close together. So I know I can definitely tell it is a strong negative linear relationship. Decreasing left to right. Now, as we get further away from negative 1, our relationship weakens. Because think about it, 0 is right in the middle, so I want to make sure if I'm going closer to 0, that's less of a stronger relationship that I have between my two variables that I'm looking at. So when we have our negative 0.65, that's like our moderate area, right in between our 0.9 and our, negative 0.3 or 0.2s. And we're going to have our points a little bit more spread out. So maybe we have something like this, where I have my points here, and we're just decreasing because we got some points here, and maybe here and here, 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 here. So points are just a little more spread out from the 0.9 to the 0.65. So it just tells you, remember the 0.9, 0.65 just tells you how strong it is. Closer it is to 0, the weaker the relationship. Same with the 0.3. We have a negative, so it tells us a negative relationship. So our points are going to be decreasing left to right. 0.3 means they're going to be pretty spread out. I mean, it's not going to be really obvious that it's negative, but it's kind of obvious it's negative. Once again, it kind of goes back to your intuition of where we're lying on the spectrum of what value we're looking at and what the strength is. So maybe I have some points that are even further apart, like this, or I have maybe 1 point in here, but I still have points that are decreasing that are more spread out. We have more area on either side where it's taking up more of that area, so it's less strong. So we have a weak negative linear relationship. All right, so fact number 4. And this is something I already talked about, but I want to reiterate. It is only 4. So the correlation only describes linear relationships. This is only linear relationships between two variables, meaning that I can draw a straight line only. A lot of you are tempted to say, hey, this forms a nice quadratic equation. It's super strong. It's a perfect negative quadratic relationship. So I would have -1. No. No, 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 no. Okay? We would have a correlation of 0 because it's not linear. This is not linear at all. Therefore, we would have an R of 0. Just because it looks like it forms some type of function doesn't necessarily mean that you're going to have a high correlation. We have a correlation of 0. Don't make this mistake. Make sure that your correlation only goes with linear relationships, not any other type of relationships. All right, next thing. Correlation does not have units. So the correlation does not have units. Correlation does not have units. Also, if you want to underline this guy, I did in my notes to make sure it only describes linear relationships, just to make sure that we're well aware that it only describes linear relationships. Lines, nothing else. Straight lines. All right, correlation does not have units, and changing the units on the axis won't affect it either. So changing the units won't affect it either. If you're taking a look at the formula, okay, we talked about what standard deviation is, we talked about what mean is, we talked about all of these different things. If you're looking at the formula, we have each individual x value minus the x bar, which is our x mean, or mean of our x values. Remember, we talked about x values, so we talked about our height. We talked about our average height. We talked about the heights that we have here. We also talked about the standard deviation of our heights. All of those are the same units. But when I divide my meters divided by my meters, or centimeters divided by centimeters, those units cancel. Same thing here. If I had number of pets here, my mean number of pets, and I have my standard deviations, the number of pets, I have pets divided by pets. Those units cancel as well. Here I just have the number of observations, like 9 observations, or 25 people, or that's 25. There's no units there. So all these units cancel out within our averaging or within our standardizing our x and our y values. So it doesn't matter what the units are. Your correlation coefficient will not change. Which brings me to my next point. Switching your units. So if I switch from height to arm span and I switch those two values like we did in the Vitruvian Man activity, I switch the two values. Well, my two values, it will not change the correlation coefficient either. So switching the explanatory and switching the response, so switching those variables will not change the correlation either. Again, looking at your values and how we are affecting in our formula, here I have my x and my y. If this was our response and this was our, this was our explanatory and our response, and we switch the two, when I multiply the two together, the order is not going to matter. If I take 3 times 2, it's going to be the same thing as 2 times 3. So the order of which we have our explanatory and response variables won't matter either. Makes no difference what you call X and what you call Y when you're calculating the correlation coefficient. The last thing that I want to discuss is this. If you have outliers, you need to be very careful about how you're utilizing your correlation coefficient because it is very strongly affected by outliers. Very strongly. Think about it. If I had some type of outlier up here or up here, it's going to weaken that relationship between my linear relationship. It's going to weaken it because it's going to pull my R value because we're looking at each individual X and Y in the calculation. So we need to make sure that when we have outliers or we don't know if there's outliers, you need to make sure that you graph it first and see if there are any outliers in your data set. That way you can either eliminate them or try not to rely on that correlation coefficient at all at that very minimum, just because it's going to be strongly affected. It's going to get pulled because in that calculation, that is what's going to pull it, regardless. So for your practice worksheet, you're going to be taking a look at a few of matching. So looking at the scatter plots and matching those correlation coefficients to your scatter plot. And then on the back, you're going to be taking a look at, just like we did in the Vitruvian Man activity, okay? You're going to be taking a look at the percentage of the women in the workforce, and you're going to be finding the correlation coefficient by hand using the table that I provide. Make sure you plug everything into the graphing calculator. So in your list 1, you're going to put all the years in your L1. L2, you're going to put all the percentages. Make sure after that you find all these values. So find your S sub Y, find your S sub X, find your X bar, find your Y bar. Remember, this is standard deviation of Y, standard deviation of X, your mean value of X, mean value of Y, and know how many people are in here. So make sure you count to your end value. So what you're going to be doing now is saying, okay, remember in your graphing calculator where we had our Vitruvian Man activity, let me pull it up. So remember, you go to your list, you go to edit, and then remember we had all of our different L1, L2, we had all of our different measurements for our height, we had all of our different measurements for our arm span. Up here is where we added in that formula. So when you go through here, I'm going to clear that out. Remember, you hit the second button. Hit the second button. I usually put parentheses first because we want to make sure we have those in parentheses because we want to tell the calculator we want to subtract those first and then divide all of that by S sub X. So I'm going to take my L1, so hit the second button, type in 1 to get L1, minus whatever our X bar is. We just plug that in. Say it's 8. It's not. And then we have, close our parentheses, and we divide by whatever S sub X is. Let's say it's 16. It's not, but that's what we would type in. And it would calculate that whole thing for us. And you do the same thing for L4, do the same thing for L5. And then it's going to tell you right here, you have the sum of the list of 5. Remember, we look at the sum of X. Look back at the Vitruvian Man activity. It tells you exactly what to do. Vitruvian Man activity. It tells you how to do all that. And then you can also check it R in your calculator. To check R in your calculator, remember all you have to do is just go back and take a look at your stats. So if you go to calculate, you go down to linear regression, you can find all those values. You got to change the list, change to L1, we'll change to L1 to L2, and we go down to calculate. This is not going to be your data. This is different data. This is data from Vitruvian Man. But remember, we look at our R value, and that's where we find our R value in the calculator. Check it. Make sure it's right. If you have questions, let me know. Other than that, we'll hand out the practice worksheet here in a little bit.